Hi, I'm Tom Bailey, a data engineer and instructor. Today we'll look at one of Snowflake's most powerful ingestion features, Snowpipe Streaming. First, we'll cover some of the theory and see exactly how it works. In the second half, we'll put that into practice by building a mini Python project. This will stream live financial transactions into Snowflake in real time. Okay, let's get started. So with the Snowflake ingestion feature Snowpipe, automatic ingestion is file-driven. A user or process uploads a file to a stage. The pipe object detects that file and then executes the copy into statement defined in the pipe body to load that file's contents into the target table. The target latency for this whole process is around 1 minute. This is from the point Snowflake receives the notification that there's a file in a stage. Now below that, we have Snowpipe's newer companion service, Snowpipe Streaming. And straight away, you can see the architecture looks a bit different. There is no stage and there are no files. Instead, a client application, and we'll get into what exactly that means shortly and see a demo, connects directly to Snowflake and pushes rows of data via a pipe into a target table. The data bypasses the staging layer entirely. And the difference in latency is quite significant. Where Snowpipe targets around a minute, Snowpipe Streaming is designed to make data available for query in as low as 5 seconds from the point of ingestion. This is the core of why Snowpipe Streaming exists. It's purpose-built for scenarios where your data arrives as a continuous stream of events or rows, rather than as periodically generated files. Think of IoT telemetry, application event logs, or live fraud detection. Situations where you can't afford to wait for files to accumulate and then be staged and loaded. All that said, Snowpipe Streaming is designed to complement Snowpipe, not replace it. If your existing upstream pipeline already generates files in cloud storage, Snowpipe is still the right tool. Snowpipe Streaming is the answer when your data source provides rows, not files. Right, let's now zoom into the Snowpipe Streaming architecture and walk through each component. Starting on the left of the diagram, the client. This is the application outside of Snowflake that is producing the data and pushing it into Snowflake. Snowflake gives you a few ways to connect here, depending on your use case and your language preference. The primary options are the Java SDK and the Python SDK. Both of these are the recommended path for most use cases and are well suited for high-throughput custom applications. The Java SDK requires Java 11 or later, and the Python SDK requires Python 3.9 or later. We'll see the Python SDK in action soon. There's also a Snowflake connector for Kafka. Apache Kafka is a widely used platform for streaming real-time event data between systems. Snowflake provides a dedicated connector that reads messages from Kafka topics and writes them directly into Snowflake tables via Snowpipe Streaming. And lastly, there is also a REST API available. Rather than installing an SDK, your application simply makes standard HTTP requests to an endpoint hosted by Snowflake, and Snowflake receives those rows and handles the rest. Because it requires no SDK installation, it's a good fit for lightweight or constrained environments like IoT sensors or edge devices, where you might not have the ability to run a full Java or Python application. Okay, once the client is connected to a Snowflake account, as part of the code, it will create something called a channel. A channel is a persistent named streaming connection between your client application and a target table. It's hosted by Snowflake, and it's where the client application initially writes its rows of data. Snowflake uses channels to give us two of Snowpipe Streaming's most important guarantees. The first guarantee is ordered ingestion. Rows are committed in the exact order they're submitted within a channel. That preservation of sequence is critical for use cases like time series data, change data capture pipelines, or audit trails, where the order of events is important. The second guarantee is exactly once delivery. To understand what that means, think about what could go wrong if the client application crashes halfway through sending data to Snowflake. When it restarts, it faces a problem. It doesn't know if a specific row or batch of rows made it in. If it plays it safe and resends the data from the last known point, it risks inserting duplicate rows. This is called at least once delivery. If it skips ahead to avoid duplicates, it risks losing data entirely. This is called at most once delivery. To prevent these scenarios, the client application attaches a marker called an offset token to each row it sends through a channel. You can think of it like a bookmark. Snowflake saves that bookmark in the channel when the data is successfully committed. So if your client crashes and restarts, it can ask Snowflake what was the last offset token you saved for this channel. The client then picks up from the very next row with no duplicates and no gaps. This is called exactly once delivery and guarantees that every row lands in Snowflake exactly once, even in the event of a crash or network interruption. So to further increase the throughput of the client application, you can optionally have more than one channel pushing data into the same target table simultaneously. This has an important impact on the guarantee of ordering. The order of the rows is only preserved within a single channel. This means that if you use one or more channel, the target table could have out-of-order records. If using multiple channels, a common pattern is to map each channel to a natural partition in your source data. For example, one channel per IoT device or one channel per Kafka topic partition, so each source's own sequence of events is preserved. Whether the rows from different channels mix in the target table matters depends on your use case. If you need strict global ordering of every row across all sources, a single channel is the right approach, but that does come with the costs of throughput benefits that multiple channels provide. Okay, and one last thing to mention about channels. They're designed to be long-lived. You should keep them open and reuse them across client restarts because that's where the offset token state lives. If a channel sits inactive for 30 days, it and its offset token metadata are automatically deleted. So let's move on to the pipe object. Rather than the pipe processing files like with Snowpipe, in Snowpipe Streaming, it acts as the processing layer for incoming rows of data. It handles schema validation against the target table, and optionally can perform in-flight transformations and pre-clustering before the data is committed. Every row ingested through Snowpipe Streaming passes through a pipe. In the context of Snowpipe Streaming, there are two types of pipe to be aware of. The first is the default pipe. This is attached to a table, and Snowflake automatically creates one of these the first time your client application requests a channel against the target table. You can view this type of pipe by running the show pipes command, but you can't create, alter, or drop it yourself as it's fully managed by Snowflake. The naming convention for the default pipe follows the pattern table name-streaming. This is important because this is how we specify the pipe when connecting via the client application, which we'll see in action shortly. The default pipe is the right choice for most straightforward ingestion scenarios and gets you up and running quickly. The trade-off being that it doesn't support in-flight transformations or pre-clustering. So if you need either of those, you need to create a custom named pipe instead. This is the second type of pipe which you can create yourself using the create pipe command. Because it's row-driven and not file-driven, we don't include the auto-ingest parameter or the from stage clause. Instead, in the from clause, we use the data source table function with the type argument set to streaming. You choose to create your own pipe when you need capabilities the default pipe doesn't support. One of the big ones is we can apply in-flight transformations using the copy command syntax. This includes filtering rows, recasting column types, and reordering or renaming columns, all of that being done as the data is being ingested. You can also enable something called pre-clustering by setting the cluster at ingest time parameter to true in your copy into statement. This will sort the incoming data according to your table's clustering keys at ingestion time, if they're defined, to improve downstream query performance on those keys. And lastly for this diagram, let's take a look at the target table. Once the pipe has processed the data, it's committed to the table and it's immediately available for querying. Snowpipe Streaming is currently insert only, so it's only appending rows to a table, not performing updates or deletes on existing data. If you need to modify or merge data after ingestion, the pattern is to land the raw records into a staging table and then use downstream continuous pipelines like dynamic tables to handle the transformation into your final reporting tables. Okay, so let's now make really clear the core characteristics and guarantees of Snowpipe Streaming that we've had a look at so far. Data ingested via Snowpipe Streaming becomes available for query in as low as 5 seconds end-to-end. This is what enables near real-time analytics use cases like near real-time dashboards that simply aren't practical with file-based loading. Snowpipe Streaming is designed to support ingestion speeds of up to 10 GB per second per table. This is the measure of throughput we can stream. And as we discussed, rows are committed in the order they're submitted within a channel. This preserves the source system's sequence of events, which is essential for time series data and CDC pipelines. The offset token mechanism ensures that each record is ingested exactly once, even in the event of client failures or network interruptions. The client application tracks the last committed offset and on recovery replays from that position with no duplicates or data loss. Snowpipe Streaming is a fully serverless feature. Snowflake manages all the compute resources for ingestion automatically. They scale based on the throughput demands of your workload. There's no user-managed virtual warehouse for you to size, provision, or manage. Now, billing is throughput-based, calculated in credits per uncompressed gigabyte of data ingested. And one last cool thing to mention is that Snowpipe Streaming can automatically adapt the target table schema to changes in the incoming data. If a new column is detected in the stream, Snowflake can add it to the table automatically. It's worth noting though that schema evolution is only supported for standard Snowflake tables. It's not supported for external tables or Apache Iceberg tables. Okay, that's it for the theory. Up next, we get hands-on and stream some transactions data into a table. Okay, so with the theory fresh in our minds, let's now get hands-on. What we're going to do is build a simple Python client application using the Snowpipe Streaming Python SDK. It will simulate a continuous stream of financial transactions and push them directly into a Snowflake table. The first thing we need to do before we touch Snowflake or write a single line of Python is generate our key pair. Snowpipe Streaming requires key pair authentication, where instead of a password, your identity is verified using a pair of cryptographic keys, one private, which you keep, and one public, which you give to Snowflake. So let's start by generating the keys. Because I'm using a Windows PC, but I want to use a Unix tool called OpenSSL to create our keys, I'll be running the following commands on git bash, which provides a bash shell on Windows. This is so these commands will work on Windows, Mac, and Linux. From within my user directory, I'm going to issue a command to create a folder called keys, and then change the working directory to that folder. I'll then paste this command, which generates a 2048-bit RSA private key and outputs it in a format Snowflake expects, saving it as rsa_key.pa. And by the way, all the files and commands required for this hands-on are available in the resources dropdown for the lecture titled Making the Most of this course. This second command derives the corresponding public key from that private key and saves it as rsa_key.pub. Once those have run, you should see both files appear in the directory you ran the commands from. One thing to point out is that these are credentials, so you'll want to keep them safe and secure, especially in a production environment. We'll be referencing the private key from our Python project, so let's go ahead and create a folder which will house our project. I'm going to create a new folder called Snowpipe Streaming Python SDK Demo Project, and then move my private key into there. Right, now that's done, let's head over to Snowsite. I'll go over to my workspace and create a new SQL file called Snowpipe Streaming Demo Setup. The first thing to do is register that public key we just generated against our user with the alter user command. Open up the rsa_key.pub file. You can do that right in PowerShell or in any text editor. What you'll see is something like a header line, a block of characters, and a footer line. We want everything in between. Copy that and paste it in as the value for the RSA public key property. So when Snowflake receives a connection from our application, it will verify the signature made by our private key against this registered public key. If they match, our identity is confirmed without a password ever being transmitted. Next, we create the database and schema that will house our data. We then create our target table, transactions. We have a transaction ID, a sequence number, a merchant name, an amount, a 3-character currency code, a status, and a timestamp. These columns map exactly to the rows our Python application will be generating. Okay, so that's all the setup we need to do on the Snowflake UI for now. I'll now move over to where we will edit and run our Python project. I'll be using Visual Studio Code with the Python extension installed. I'll open up the project directory I created earlier. You can see our private key in our root directory here. I'll start by creating a new file called profile.json. This is the connection configuration file that the SDK reads to know how and where to connect. We have the username, the account identifier, and the full account URL. Then we have the location of our private key file. And because I moved that into the project's root directory, I can just reference the file name directly. And finally, we have the role, account admin. This is the role I use to create the database, schema, and table. So for simplicity, I'll also use it here. As we know, account admin is a highly privileged role, and outside an educational context, the recommended practice would be to create a dedicated role with only the specific privileges needed. Okay, now for the main event. I'll create a new file called transactions.py which will hold our client application code. This isn't a Python tutorial, so I won't be narrating every single line, but we will talk through the most important components. The first thing to point out is where we import the streaming ingest client class from the Snowpipe Streaming library. This is the class that handles the connection to Snowflake, opens our channel, and gives us the method to append rows to that channel. But we currently don't have the Snowpipe Streaming library installed. To keep our dependencies isolated to this project, let's first create a virtual environment. Hit Ctrl-Shift-P to open the command palette and type Python create environment. Select Virtual Environment and then choose your Python interpreter. I'm selecting Python 3.10 here. As we mentioned previously, the Snowpipe Streaming Python SDK requires a minimum of Python 3.9. Let's then open a new terminal by going to Terminal and New Terminal. Once it starts, you'll see it using the virtual environment we created. Then I'll run pip install Snowpipe Streaming. Okay, good. That's done and we can close down this terminal. So the job of this Python file is to simulate a continuous stream of financial transactions and push them into Snowflake. Up at the top, we have our constants. The database, schema, and table name match exactly what we created in Snowsight. Then we have this pipe variable. As we covered in the theory, the first time a client requests a channel against a table, Snowflake automatically creates a default pipe for that table. This will follow the naming convention of table name, hyphen, and then streaming. So ours will be called transactions-streaming. Snowflake creates it behind the scenes. We just need to reference it here so the SDK knows which pipe to route our rows through. Okay, scrolling down, we have a function called makeTransaction. This builds a single row as a Python dictionary, each key mapping to a column in our transactions table. That dictionary is what gets pushed into Snowflake as a row. Now going down a bit more, we have the main function. This is where the SDK does its work. We initialize the streaming ingest client, passing in our target objects and pointing it to our profile.json for authentication. Then using the client object that class created, I open a channel by using a fixed channel name, transactions_simulator. This returns both the channel object and its current status. From that status, we retrieve the latest committed offset token, the bookmark Snowflake has saved for this channel. If a token exists, meaning this channel has been used before, we set our starting sequence number to 1 beyond the last committed offset. If no token exists, like in this case, meaning this is a fresh channel, we start from 0. This is the exactly once delivery guarantee in action. Rather than blindly starting from the beginning on a restart, the client asks Snowflake where it got to and then resumes from the very next row. Then in the loop, with each iteration, we append a row to the channel with the append row function. We pass the row as a dictionary and then the sequence number as the offset token. Snowflake commits that through the pipe and then into the table. Okay, let's finally run it. I'll go up here to the top right and click Run Python File. We can see the channel open and the terminal begin to print transactions, the timestamp, the sequence number, merchant, currency, amount, and status. Each one of those lines represents a row being pushed through the channel, through the pipe, and committed to our transactions table in Snowflake. And the SDK can handle a throughput of up to 10 gigabytes per second per table. This is just a simplified example to show the flow clearly. I'll leave it running and jump back over to Snowsight. Here we'll write a simple query to select all the rows from our transaction table and order it by sequence, descending order. And there we go, we can see the rows in the table already. Now if we run that after a few more seconds, you'll see that the row count has gone up. The data is landing in near real time. New rows are appearing in the table within seconds of the Python script pushing them through. That is the 5-second latency we talked about in the theory. There's no file being written, no stage being polled, no copy into being triggered. The rows are going directly from our Python application through the channel, through the pipe, and into this table. Okay, let's go back to the terminal in Visual Studio Code. I'll now simulate a crash by pressing Ctrl+C. You'll see it errored out with keyboard interrupt. If we read the table, we can see the last committed row was sequence 21. If we run the script again, we should see that it prints out that it's resuming from where it left off at sequence 22. Running the select one more time and you'll see the order has been preserved and nothing is missing. Okay, there's one last thing I want to do before we finish, and that is to give you a sense of the throughput it can handle. In this script, I set the wait interval between row uploads to 6 seconds. Let's go in and change that to a fraction of a second. If I kick this off again, you'll start to get a sense of how many rows we can upload to a table. Bear in mind, if we remove the wait entirely and had multiple channels, the throughput could be increased even more. Okay, so there we have it, the full end-to-end flow. Key pair generation, the Snowflake setup, a Python client application streaming rows through a channel into a table, and querying that data updating in near real time. Thanks for watching, and I'll see you in the next one.